Our fourth awardee for technology innovation and presenter is Dr. Ted Moise. He's manager of Analog Technology Development Group at Texas Instruments. Dr. Moise got his BS in Physics and Engineering from Trinity College in Hartford, Connecticut, and Ph.D. from Yale in 1992. He got tired of cold weather, maybe, and joined TI in Dallas in 1992. Now, while he's coming here, just a little tidbit, we're familiar with random access memory. You know, that's what I know about RAM. Well, he added F, not a word, just a letter, and call it FRAM, which is making a world of difference in performance of memory. Please, he will explain all his work.
Thank you. Okay, very good. Thank you very much. It's a great honor to receive this award. I'm very, very happy to receive it. I'm also very happy to attend this prestigious conference. It's been extremely interesting today. And finally, I realize that I am the last talk between you and the reception. So I'm aware of that, and I'll try to keep it going along. Okay, so I'm going to start off by talking about semiconductor technology. I'm going to try to give a brief overview of 50 years of innovation. Then I'm going to transition from that into ferroelectric memory. What is it? What does the F stand for? I'm going to talk a little bit about the wafer and the die and the cross-section, a little bit of the materials and device physics. And after that, I'm going to talk about some of the applications. Okay, so everybody's familiar with semiconductors. We carry them all the time. So in preparation for this talk, I wanted to somehow discuss about how semiconductors have changed over 50 years or so. So I decided to use the Apollo guidance computer as an example of state-of-the-art technology in 1967, and compare that to the Apple iPhone as consumer technology in 2011. So if you compare it, the number of logic gates, which is the heart of the digital system, for the Apollo guidance computer is 5,600. Compare the Apple iPhone, which has 1 billion. The RAM that you just mentioned, there were 2 kilobytes on the Apollo guidance computer as opposed to 512 megabytes on your iPhone. For the non-volatile memory, which is the part that stores the information, stores the code to operate the device, and can hold that information even when the power's off, that's gone from 8 kilobytes on the Apollo guidance computer up to 32 gigabytes. And that stores not only the code, but the movies and the music and the pictures and everything else. And all this is really, really impressive. But the most impressive one is the cost. If you look down here, what you see is that the cost of a transistor in 1967 was around 10 cents or so. As compared to now, the cost of the transistor is 0.01 microdollars. So it's changed by a factor of 10 to the 7th over 44 years. Okay, a factor of 10 million. And that's what allows us to walk around today carrying tens of billions of transistors with us. You know, 20 years ago, 30 years ago, we'd carry around a transistor radio that had a few, but now we carry around our iPhones that have billions and billions. So that's one interesting aspect I want to mention. The other one that I want to mention is, if you look at the back of this Apollo guidance computer, what you would see is this rack full of wires. And these wires physically connected one logic gate to the next. Okay, and you can imagine if there's 5,600 of them, it gets very, very complex. If you tear open your iPhone and mess up the warranty on it, what you'll see are a bunch of black plastic packages. And whenever you've opened up an electronics device, that's what you've seen. And inside those black plastic packages are chips. And those chips have maybe one chip, maybe multiple chips in each of those packages. And each of those chips have different layers of metal that are used to conduct the signals from one transistor to the other. And the more complex chips have 7, 8, 9 layers of metal. So all this wiring has gone from being done from a single wire going from a transistor to transistor to all being done in the chips itself. Okay? So this phenomenal change is known as Moore's law. Everybody's probably familiar with that. That is, the number of transistors has increased by a factor of 2 every 2 years. And this CMOS scaling makes most digital circuits inexpensive now. You know, you buy a computer, it's pretty cheap. You buy most electronics, they're pretty cheap. So for a company like TI to survive, we can't just scale. We have to do something beyond that. We need to differentiate and add value. And the way we do that at TI is by focusing on analog products and embedded processing products. That is, products where we make systems on a chip. And so the kind of things that we focus on are analog for high precision, like ADC converters, RF for speed, high voltage and high current for power management. So the battery packs in your phones and your computers all have TI chips in them. We focus also on ultra-low power for extending battery life, or even operating without a battery. We work on sensors to monitor the environment. And all of these more complex devices require non-volatile memory, because all those devices need some type of code in there to explain to the digital circuit what to do and somewhere to store the data. And so at TI, we've developed this embedded ferroelectric memory as a very good counterpart to this wide range of devices. And it makes it much easier than some of the conventional memories. So let me talk a little bit about what ferroelectric memory is. A ferroelectric is just a crystal whose spontaneous polarization can be reversed by the application of electric field. They've been around for years. They're used in actuators. They're used everywhere. Now, what that really means is that there's a small dipole in the crystal. In this case, it's a PZT crystal, that's zirconate titanate. This titanium or zirconium atom is offset from these oxygen, and that dipole produces an electric field. And you can change the sense of that dipole by the application of electric field. So we store 1 in one orientation and 0 in the other orientation. This happens very quickly. You can change the state very quickly, and you can do it with very low power. So it's a fast write, low-powered memory. It replaces battery-backed SRAMs, and this concept is really from the 1950s. People have been trying to do this for a very long time, and finally the technology has caught up with the concept. Okay, so let me talk a little bit more about ferroelectrics. This is an example wafer with embedded FRAM on it. So this is an 8-inch wafer, 200 millimeters, about 8 inch. A typical device is around 10 millimeters squared. There's about 2,500 devices on a wafer. So about 20 billion transistors, 18 billion capacitors. It takes about 300 manufacturing steps to create this. And this is manufactured right in Dallas. And as Mayor Parker pointed out, I guess it's the 3rd largest city. But the manufacturing is done in Texas. So now, if we click on this, there's a little bit of a 3D movie here. And the wafer rotates around a little bit. And then we're going to zoom in and look at a specific die. And we're going to go ahead and expand that die so I can talk about what happens a little more at the micro level. So in this case, we have a die that's around 10 millimeters squared. And at the outside of this die, you see these silverish pads. They're actually aluminum bond pads that are about 60 microns by 60 microns wide. Each of these, what we do is we attach a wire to each of these bond pads and bring them out to the outside of this, to the another part of this ubiquitous black plastic package that you see with all the electronics. This die itself, there's a memory bank up here and a memory bank down here. So if we dive into this a little more, what you can see now is that the memory banks are labeled, the top block of 4 megabit, the bottom block of 4 megabit. There's a spine that controls it. This segment right here is 32 kilobit, and there's some decoders and word line drivers, et cetera, et cetera. And this chip itself will replace a 4 megabit or 8 megabit battery-backed SRAM without the battery. Okay, so it's very useful in that sense. So let's dive into this a little more so I can talk about the technology. So we're going to rotate around again using the 3D graphics. We're going to get to the edge of the die, and then we're going to dive into it. So when we do that, what you can see here is a cross-section of the device. Now in reality, this substrate's about 200 microns thick, so the vast majority of it's way down here, but we're just concentrating on the upper few microns of it. So this device has the substrate and the transistors are here, and here are the metal levels which interconnect all the transistors. And what we've done in this program is to embed between these transistors and metal 1 this layer of ferroelectric capacitors. Okay? No one else in the world has this process right now except TI. So these ferroelectric capacitors, what they do is they can store in a non-volatile way. So you can write them, you can write the data into these capacitors, and they can turn the power off and you still have the data there. Okay? So let me talk about this in just a little more detail. So here's a picture if we blow up those capacitors, expand it a little bit of the actual materials involved. So the key is this PZT ferroelectric here. This stands for lead zirconate titanate. And it's about 700 angstroms thick, and it's deposited on an iridium electrode. And iridium is a very expensive material. Why in the world would we use iridium? Well, it ends up that PZT is deposited at a high temperature, around 600 degrees Celsius, in oxygen. And there are only so many materials that you can expose to oxygen at 600 degrees C without them oxidizing and becoming an insulator themselves, which we can't have for a ferroelectric. So we can only use the noble metals like iridium or platinum or a complex oxide electrode. And we chose iridium. That ends up being the best choice. So we have iridium on top and bottom of this PZT, and then we have these titanium nitride barrier layers on the top and bottom. Those are conducting. So we can bring a signal all the way down from the metal through the capacitor down to the transistors. And we've also encapsulated these capacitors with aluminum oxide around them. Now it ends up that PZT and all ferroelectrics are very, very sensitive to hydrogen. If you put hydrogen in there, it starts reacting and destroying the ferroelectricity. So this aluminum oxide around the capacitor inhibits the diffusion of hydrogen into the capacitor. So we've created a capacitor that's completely isolated in terms of hydrogen diffusion, both on the top and bottom and on the sides. And that was really one of the big tricks in making this technology work. And that's been one of the big issues with it over the years, because there's a ton of hydrogen in semiconductor processing, and you need to somehow keep this capacitor of high quality in that ambient. Okay, so let me talk a little bit about electrical properties. How does it work? I'll get back to this, this picture here of my unit cell with these titanium or zirconium atoms. And you can see there's two stable states thermodynamically, one positive, one negative. And if you look at this on a hysteresis curve, you can map this out as a function of polarization versus electric field. So here would be the positive data state and the negative data state here. Now this hysteresis curve is very reminiscent of the ferromagnetic hysteresis curve, which is magnetism versus magnetic field, except this is polarization versus electric field. Okay? So because of that analogy, when researchers first discovered this effect, they call it a ferroelectric, because it looks very much like that of a hysteresis curve of ferromagnet. But the problem with that is that there's no iron and there's no magnetic field. So it confuses everybody. So this is a ferroelectric, is a completely dipole electric field effect device. There's no iron, there's no magnets. Okay, but it's very, very confusing. Okay, so let's talk a little bit about how it works. So let's say we start off down here at this point, and we put a positive voltage on it. As we do that, we go along this part of the hysteresis curve. And if you look at the magenta part of the curve here, you get a large spike in output current. Because essentially what's happening is you're switching the sense of that dipole. In order to keep the capacitor charge neutral, you have to bring electrons into the electrodes. So if you take the electric field off, you're back over here. So now the next time you do it, apply a positive pulse, you go from here to here, and you get a small amount of current out, because you don't have to switch the sense of that dielectric. That ferroelectric rather. So when we switch the sense of that ferroelectric, we call that a data 1. When we don't, we call it a data 0. And now the trick is to put millions of these things in a circuit and have them all work the same way. And I'll mention that this switching, by the way, occurs very quickly. Intrinsically, the switching occurs around 300 to 400 picoseconds. Okay, so when we first started doing this, after a couple years, we got a bit distribution like this. So this is essentially the distribution of zeros in the black here as a function of voltage and the distribution of ones. Looks pretty good. There's separation between the zeros. There's a distance between the median 0 and a median 1. And this was great to start writing papers and go to conferences and stuff like that. But the problem is that it's nowhere near good enough to make an actual product. Because if you look down here, you've got a bunch of ones that can be confused to zeros and a bunch of zeros that can be confused by ones. So we figured, okay, well, how hard can this be? So go on 3 years later. And here we have, now on a log scale, this distribution in the yellow, where all the zeros come down to here, and there's a little bit of separation before the ones start going up. And we introduced a repair scheme so that we can get rid of these weaker bits. And using this repair scheme, we could kind of start sampling product, but still really wasn't good enough. So keep going further, a couple years later, and now finally we get a distribution that looks much better. Here are the data 0s, and here are the data 1s. Nice separation to bottom, and this is good enough to start qualifying a product. And so the point here is that when we first started making these things, it took about 10% of the effort to get 90% of the bits working the way you wanted them to. But to actually get the product to work, we had to expend the other 90% of the effort to get the bottom of that distribution work the way it needs to. Okay, so part of it's just getting the distribution correct. The rest of it is retention and cycling and making sure the reliability is good. This type of memory really likes to be cycled, unlike usual flash-based non-volatile memory. We've extrapolated the cycling endurance out to 2 times 10 to the 15th cycles. So what that means is that if you wrote data into one word of this memory at 1 megahertz, you could keep writing it for 65 years without ever wearing it out. Okay, so it's essentially infinite. You can just keep writing it. It really likes to be written. The other part of a non-volatile memory has to store data. So we've done some extrapolations as a function of temperature and time, and all of the products that we have out there now retain data for greater than 10 years at 85C, and some of them operate at even up to 125C. And this is something we continually get asked about. Can we go to higher and higher temperatures? And it's something that we're working on. And the weakest bits here determine the reliability limits. So we absolutely had to fix those weak bits in order to make this whole memory work. Okay, so now let's talk a little bit about applications. One that TI announced last year is this ultra-low power microcontroller. Microcontrollers are basically small computers on a chip. And it's a very large market, even though it's a small computer. It's around $15 billion a year in semiconductor sales. And it's used from everything from your smart coffee maker and dishwasher to the analog brakes in your car. Okay, so it's a very, very widely used device. So here's a comparison between a microcontroller that was created using embedded FRAM as a memory in the green versus embedded flash, which is a typical approach in the red. Because of the fast writes of embedded FRAM, what you can see is you have about 100 times faster throughput data writing into the FRAM than the flash at about 1/3 the current. Another way to look at that is if you write at the fastest speed that the flash can handle, which in this case is about 13 kilobytes per second, you have 100x current reduction. So if you want to match the performance of what you had right now, this is a memory that offers in active mode about 100x current reduction when you're writing data. So this is right now the lowest power microcontroller on the market, and we continue to improve it, and there's going to be other versions coming out soon. So that's one specific application. Here's a whole series of applications in this Venn diagram. I won't go over all of them. I'll just mention this industrial control case here. If you have an assembly line that's all robotic, you need to continually write positional data to a non-volatile memory, because if you have a power glitch or you lose power, you want those robots to come back in a known state without damaging all the WIP. Okay, so you have to have some kind of system to do that. There's similar crash recorders in cars that do similar things. On the right there, in terms of ultra-low power, we have some activities now to replace SRAMs in pacemakers. If you have a pacemaker and you want to store EKG information, what happens is that you end up using a lot of the battery life of your pacemaker just to store that information and keep that information in the SRAM. So you end up having a problem if you want to put more and more memory in there, that your battery life goes further and further down. So by replacing that SRAM with FRAM, you can put more memory in the pacemaker, and you use less power and have longer battery life. Okay. So, you know, this program's been going on for quite a while, and recently, the marketing team from TI got a hold of it, and I don't think any of these guys are over 35. And so, when they got a hold of it, they turned it into this. Okay. YouTube video. So up to this point, I've talked a little about semiconductor technology. I've talked about FRAM technology, talked a little bit about the applications. So I really have one slide left, and I'm going to talk a little bit about the journey in order to create this technology. And to use that, I'm going to use this construct. Somebody mentioned a roller coaster, an enthusiasm roller coaster. And this ranges from despair to ecstasy, okay, as a function of time. So when the research was first approved in 1997, there were basically 2 of us working on the program. We were ecstatic. Hey, great. We have a new program. We're very excited about it. And this was in the Central Research Labs of TI. After a couple years of work, or a year or so of work, we demonstrated some very low voltage capacitors using a new deposition technique, MOCVD PZT, which nobody had done before. Published some nice stuff. We were very excited about it. Then the equipment broke. And there was no capital money to replace it. Well, this is, disappointing, but maybe we can figure it out. Then TI sold its memory business. Now, if you're developing a non-volatile memory and your company sells its memory business, that's not good. So we had to explain to management and justify that this was really not a commodity memory for use in standalone. It's really an embedded memory, and focus it along that way. And meanwhile, we also talked to some other companies and formed a joint development program. And that JDP allowed us to get resources in from different folks and different groups, and we actually moved the team, including myself, out to California, and started working on it there. And we had some good success. Made some really small capacitors. Those, again, some nice publications. Things were looking good, okay? We got some momentum going again. Then we lost our driver customer. And that's not good, because without a driver customer in a big company, you're in deep trouble. So we talked around to folks, went this way and that way, and found another driver customer, and got some prototypes out that worked. So that's encouraging again. A little longer, we got the product yield up, the end customer's happy. Hey, this might actually work. Everybody's feeling pretty positive. And then the reliability fails came in. We had retention issues and things that had to be resolved. And that took a long time to fix, but fortunately we had some patient customers. And we finally got reliability to pass, and our first products came out. Okay, so from when we started in 1997, our first products were manufactured in 2007. And by 2011, now 4 years later, we've shipped almost 100 million devices. Okay, the bulk of which have been in the last 12 months. So it's really starting to ramp up. And the key message here is that there are going to be ups and downs, and you have to somehow figure out a way to keep things moving ahead if you're committed enough and you believe enough in what you're doing. And this graphic I've used a lot over the years. You just can't give up. So like this frog, you just hold on tight and try not to get swallowed by the heron. Okay? And eventually he'll give up and let you go. Okay? So in summary then, the transistor cost has been reduced by about a factor of 10 million over the last 44 years. And that more or less coincides with Moore's law. 2 to the 22 is 4 million, so it's about right. Embedded ferroelectric memory is now in mass production. It works. It's out there in many applications, and maybe even in the car that you're driving. About 10%, when you're actually making a technology, about 10% of the bits, the lowest 10%, the weakest 10% of stuff take all the effort, okay? Making a median bit work, making the average of something work is really not that, is hard, but it's not the main part of actually making a product. There are many applications for embedded memory, embedded ferroelectric memory, and finally, if you're going to create a new technology, it's a roller coaster ride. You got to stay focused, hang on tight, and try to enjoy it when you can. Okay. Thank you very much.
Questions?
There's a very controversial futurologist, Ray Kurzweil, that said that the future of computer is linked to transistors, as you said, and that eventually we're going to be able to produce so much information and store so much information that eventually the bottleneck is going to be us, our memory that doesn't expand at the speed of computer's memory. So my question is, in a future that is not too far, where the amount of information is becoming grower and grower, controlling that information is key. What is that the computer industry is doing in that sense, and how can we think of an interaction between human brains and memory and computer brains and memories?
I feel we've already hit that point. Sometimes when I look at my email. And that's really not my specific area, but I know many folks are working on detailed information mining approaches and try to rip out the nuggets of the really critical information from the mass of not so critical information. And I think there's going to be some very relevant kind of software techniques and coding that will have to be done over the years.
Yeah, I'm not very proud of this question, but I'm just curious when I see your last picture. Where's the IP generation in that, and how much longer do you control it?
Well, the IP generation is in the creation...
Time-wise.
Time-wise,
yeah.
okay. So we started, our first patents were probably in 2000, 2001 time frame, so 17 years after that. We have a continual stream of patents, though, that kind of go on from there. Okay. Thank you.